This is the actual recording with the PowerPoint in it, and here we are going to get that screen shared with you guys in just a second. We're talking about functions again today. We're talking about recursion, prototypes, so let's get into it without further ado. Okay, so function prototypes. Does anyone know what a function prototype is? Anyone want to tell me what they think a function prototype is? Comment in chat. Basically, in C++, if you don't define your function before the main function, okay, like we had in Code Light, I can show you an example from last week with our function guest list that we made. So here we had a guest list that we were printing, and our main function is at the very bottom, and you can see we call the print guest list function and the clear guest list function. Here, the print guest list function and the clear guest list functions are defined at the top of the program. So the compiler knows what this function expects in terms of arguments, which is 3 strings, and what this function expects in terms of arguments, which is 3 strings. However, if I move these, okay, below, and then I try to call or start typing print underscore guest, it doesn't know what it is. It can't give me reference to it. It can't help me out. Print underscore guest, like it's not there. And even if I go into here, it won't tell me what it's expecting, right? Sure, G1, G2, G3 come up because those are the only variables I have. But compare and contrast, if I move these back up to the top of the function, or sorry, the top of the program, the main.cpp, if I start typing this again, print, there, look at that. I get auto hinting, and it tells me what's expected in the arguments. A const of string with a reference type variable. Const string reference type variable, const string reference type variable. And it tells me, I can just hit tab and boom, look at that. It knows that there's 3 const string reference type variables. I can just hit tab, 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 and go through those. And it tells me with the auto hinting feature. So that is only in C++ because I've defined these at the top. Let's say that I had defined these somewhere else, though, or they're at the bottom or whatever. That is where function prototypes tell the compiler what it needs to know about a function before it's used, even if it's defined at the bottom of your class or your main.cpp. So you define the function at the top of the function prototype before you call them. That's one way to do it. Or the other way to do it, because that's not a very practical solution for larger programs, is to use function prototypes, which tells the compiler what it needs to know. It also is called forward declaration. So sometimes you'll hear that if you're looking online. You place it at the very beginning of your program, or you can use a header file, which we'll talk more about later today. All right, so an example of a function prototype. So here, the second one, that's what we're used to. That's the actual function definition. So we've got function name, it returns an int, and then there's our statements, our logic in it. The prototype is just this, int function name. Done. Okay, now if you actually have arguments you're passing to a function that's expecting, int function name int a, right? So here's our function. It's actually expecting an int. You can do one of two things. You can just say the type of variable it's expecting, or you can give it a name. In this case, the name of the int it's expecting is a, the letter a. So you can do one of two, and that's what that question in the quiz was talking about today, where it's saying it's not required that they have names. You just have to say the type. Okay, so there's the function definition, but the prototype is just a very basic example that tells the compiler the return type, the name, the expected argument types. Okay, and you put that at the top of the program, and that way the compiler can help you out. Okay, and I'll give you an example in Code Light here so that we can kind of see how the prototypes actually help us out here. So the compiler doesn't care about the name of the arguments, just the type. So let's say I move these two functions, print guest list and clear guest list. I cut them underneath my main, okay? So as I'm typing in my main, look, I'm getting an error because it's saying, what the heck is this? An undeclared identifier print guest list. If I try to call print guest list again, I'm not getting any help or auto hinting, okay? There's nothing there. So what we want to do is we want to create our Oops, our function prototypes here at the top of the class or the top of the main.cpp, so the compiler knows what it's expecting. So our first function is called print guest list, and it's a return type of void. So we do void print underscore guest underscore list. Okay, and does it expect anything? What does it expect? It expects a const string. Okay, and we don't need to give it a name. We just need to give it the type of variables it's expecting. So whoops, I forgot the letter C. Const string, const string, const string. Whoops, I forgot the letter C on all of them. Okay, and then we close it off, and a semicolon is needed. Okay, and that is our prototype. So if I save this, look at print guest list. The errors that were besides these go away now. And if I try to start typing print underscore guest list, look, I get the auto hinting back. And if I hit tab, it tells me what arguments are needed to be supplied for that function. Okay, cool. So candidate function not viable requires the arguments but 0 were provided. No matching function to call print underscore guest list. I believe that's fine. So if I run this, I'm going to make one for clear guest list as well. Void clear guest list. It also expects the same functions, except they're not consts. So we've got this. Boom, boom, boom. And semicolon. All right. And there we go. That error went away, whatever that error was, because I didn't have my prototypes for both of my functions. Now I've got prototypes for both functions that are defined in the bottom of my program. And my main function here that calls print guest list and clear guest list is happy because it has the prototypes that the compiler can reference. And if I run it, then we're good to go. And look at that. Whoops, that's not my active program. Look at that. There we go. Bring my thing over. There's our guest list, right, from last week. Okay, cool. So that is how function prototypes work. That's an example. Here's one last example. So if you have a void function, like we just did, then you just do void. That's the return type, function name, and then empty arguments if there's no parameters expected. Very good. Any questions about function prototypes? Some more examples here. If you're expecting an int and a string, you can just do the types, int and string, or the name if you actually want to give it a name, int A, string B. You don't need to give it the name, so just remember that. Either one of these prototypes is valid. You can just give the types or the names. Cool. So now actually calling a function. So we have a function here called say hello, right? And this is our function prototype at the top. So it's a return type void, say hello, and it expects no parameters. So our compiler knows that. So if we try to call it and pass it 100, it'll give us an error because it knows, the compiler knows it's not expecting a 100. It's not expecting an int. So same thing, if I go to my code light and I try to call print guest list, right, and I try to pass it, instead of trying to pass it a string, let's say I pass it an int. We're going to get an error even before I do anything. It's going to say, listen, there's no matching function called print guest list that accepts integers. It requires 3 arguments, but 0 of the requested argument type were given. 0 were provided. So even if I save this, look at, we're going to get an error. If I try to run it, it's not going to like it. It's going to say invalid initialization of reference type const string. So it knows because I gave it a prototype of const string, that's what it's expecting down here. So the function prototypes are very, very handy. It's highly recommended you do them. I know it's a little bit of extra work, but for bigger programs, it really helps you out with the debugging, testing, and error handling from the program. So again, here we can see that the void is the return type. So when we try to return the say hello function into the console with the extraction operator, it's going to error because there's no return value. So there's no string that gets returned from this. So obviously you can't print anything to the console. Cool. Next thing I want to talk about is kind of a specific thing as well, getting down and dirty into functions. If you want to pass an array to a function, we can pass an array to a function by providing the square brackets in the formal parameter description. So what that means is when you call a function, if you want to pass an array, if it's expecting an array, you just add those square brackets, right? So the array elements are not copied. That's something to remember with arrays. They're that reference to memory. Remember, it prints a hex value. You just print the array name itself. It prints a hex value to the address location in memory. And so when you pass an array, they're not copied. So if you change those elements, they're changing the actual values in memory. So the location in memory will be what's evaluated. All right. So if the function has no idea how many elements are in the array and it only knows the location of the first element, what we need to be able to do is actually pass the amount of elements in the array. So here we can see I've got a function prototype called print array. It's a return type void, and it expects an array of integers. Okay, and here we've passed it square brackets because we don't know the size. So when I'm in my print array function, okay, I don't know how many elements are in my array. I don't know how to loop through. I don't know how many, right? I called it here and I passed the array my numbers 1, 2, 3, 4, 5, but there's nothing I don't know the size. I can't loop through anything, right? So what we need to do is actually add a second parameter, a second argument to this prototype. So here's the prototype. It's a void return type, but now we're passing something called size underscore t, and it's actually that's the variable type size underscore t, and we just called it size. So here we pass my numbers array. Okay, so that's what the array is called, and we're passing the size of 5 because we know it has 5 elements. Remember, with arrays, you hard code the value because they don't automatically update like vectors. Now with a vector, when you pass it to a function, you can obviously use the function, the vector methods like dot size, so you don't have to worry about it. But with arrays, there's more of an oddity with a specific way that you need to pass the size of the array to the actual function. So here we can see the function print array, and we have passed it the size, and now we can go in a for loop and look at the actual size variable that we were passed, which was 5, and we would loop through our array elements, right? Now, let's say we don't want to actually change the elements or the values of what's in our array. What we have to do is we have to use consts. So we'll talk about that on the next slide. Just about what this slide is mentioning is just an example if we wanted to have a function that zeroed out or reset our array back to 0 for every element. So it actually is modifying the address in memory, so it's not making a copy. So if you want to reset everything back to 0, say you had the user enter 5 of their favorite numbers, and now you want to reset it and store a new set of numbers, then here we go. We've got our 0 array function, which is going to be the reset function. We loop through whatever the size of our array was. So if our size of our array was 5, that's the number that's passed. We loop through it 5 times, and then we set each index, each element to 0, and that's what zeroes out the array. Now, if we don't want to change any of the actual values in our function, what we have to do is tell the compiler that the parameters are consts, right? Constants are read-only, they can't be changed. This is really useful if you want to have a print function, because all you want to be able to do is read from it. You don't want to be able to change any of the values. So the const keyword is used here on our print array method or function. And here we can see we've made our array a const of numbers, of integers. We pass the size still, we loop through it still, but then we just print them out to the console. Any attempt to change it, so if you had a setting it to 0 or something, will just give you an error. So it's really helpful to do that kind of stuff. If you know you don't want to actually ever change it, then just do the const keyword. It's really quick to do that. And then in the future, if you ever try to make a change, it'll error out on you and it'll stop you from making a change where you don't want to make a change. Cool. Hopefully there's no questions on that, because then we'll move on to recursion. If there's any questions, just let me know. It should be pretty straightforward. Cool. All right. So recursive functions. Does anyone have any experience? Okay, thanks, Raymond. Does anyone have any experience with recursion or recursive functions? I know it says it on the screen here what it is, but if you have experience, do you mind telling me in a quick sentence or two what you might use recursion for, what a recursive problem is, why you would use it, or what, yeah, just what it is? Take that as a no. Okay, cool. So a recursive function is a function that calls itself from within itself. And I know it sounds a little bit like Inception kind of thing, a dream within a dream or something like that, but that's basically what it is. So either directly or indirectly through another function, it's calling itself. Okay, so recursive problem solving is a really helpful type of problem solving that programmers can have, a lot of trouble when they first learn it, and that's totally normal because it can be a little bit of this inception-y, mess with your head and recursion. It sounds kind of confusing. Eventually, you'll understand that recursive solutions make sense in certain scenarios, and there's many types of recursive problems that lend themselves well to a recursive solution. Okay, so basically what recursion is if you have two or more activation records on the stack, if you're looking at your call stack, for the same function, then basically you have recursion. Okay, so an example of a solution, a recursive solution that would lend itself well, in mathematics, we have factorials, Fibonacci's, fractals, etc., where it's like a repeating problem. If you've ever taken math or heard about Fibonacci or any of those things, you'll understand kind of what I'm getting at. So basically, searching and sorting, we have stuff like binary search and sort, where it will search trees or do a depth first search or graph it and many more, right? There's another problem called it's a classic problem called the Towers of Hanoi that can be really hard to solve without using recursion or trying to come up with a non-recursive solution. So let's see how we can calculate the factorial of a number using recursion, right? This is a basic example, but you can use this ideology of recursion, I guess, or this template for recursion for really difficult solutions in the future. So let's take a look with the example of factorial. So in math, we have something called a base case. So the base case is as long as the number is 0, so factorial of 0, it's 1 equals 1, okay? So that's our base case. And you always need a base case because that's how you exit from having to have an infinite loop, okay? Now, the recursive cases, which just means they repeat in on themselves forever and ever, is basically a factorial of n, or n factorial, is equal to n times n minus 1, right? And that is where the recursion happens. So n is equal to n times n minus 1. So if you have 3, then 3 times 3 minus 1, which is 2. So 3 times 2 is 6. So we're doing the factorial of 3 here. So 3 times 2 is 6. And now you have 2. 2 minus 1 is 2. So then the factorial of 3 ends up going through all of the numbers from 3 to 0 until n equals 0. And then you get your final number. So you can get some really massive numbers with factorials. And we'll actually do an example here in Code Light. And we'll actually look at what that might look like, okay? So let's open up our Code Light here. Make a new project. And you can follow along with me here if you want. I'm just going to call it Week 9 Recursion. Okay? Set that to my active project by double clicking it and open the main.cpp here. And right away, we'll just do using namespace std and get rid of these two things. Give us a little bit of space. Okay, cool. So because we've talked about functions already a little bit, I'm going to make a function. I'm going to start off with a function that's going to return an integer, but not just any integer. I want it to return the largest type of integer possible, since with factorials, you can end up with huge numbers, right? So, for example, the factorial of just the single number 8 gives you the number 40,320. And we're going to look at that example right now. So the largest type of an integer, if you remember us talking about sizes, is long. Okay, so we're going to do an unsigned because you can't have negative numbers, right? As soon as it hits our base case, which is 0, it exits the loop. So long is going to be what it returns, and then our name of our function is going to be factorial. Now, the expected number that we expect when we're calling the function will also be an int, and we're going to also expect an unsigned long. And we're going to call that n, right? Just to stay in tune with what we just looked at for the math example here. Okay, we're going to call it n, and we're going to follow this exact mathematical pattern. All right, so from here, we haven't put any code in here, but I will comment and say this will be a recursive problem for solving factorials. Now, from our main, we want to call the factorial function. Okay, so all we want to do, because it's going to return the int, we can save it into the console so we can output whatever's returned all in one line. So factorial, and because it's expecting an unsigned long of n, we're going to pass it the number 8. Okay, and then end our line. Okay, and this should equal, because I've done this before, should equal 40,230. Okay, and then as with every expression in our main, we have to return 0. Whoops, so we don't get any errors. Okay, so let's add our actual logic to the factorial function. So if n equals 0, okay, that is what's called our base case. So as long as it's equal to 0, then the factorial of 0 is 1, then we will exit the program. So as soon as we get down to the lowest number, which is if it equals 0, return 1. So because we're returning an unsigned long, and we're going to output it to the console, we know that the factorial of 0 is 1. We're going to return 1 to the console. So we can test this. Okay. Else, okay, so we don't have to actually have braces here because I'm just doing one line. But basically, if n is not 0, then other code. I don't even have to write else, because basically we just tab it in one line, and that will be the if statement if n triggers as 0. Else other code here. Okay, and I'll do this here after. But let's test this. Week 9 recursion. And I'm gonna run it here. Whoops. Look at that. We returned 1. Perfect. And that works because we know that the factorial of 0 is 1. Okay, so let's do our other code here. So we want to return n times. Now, how do we call n times n minus 1? Well, it would look something like this. N times, and then we call the function within itself. So that's the recursion, right? Because we're calling a function from within a function, n minus 1. Okay, because you can't just do this, because then it will only do it once. Okay? So if you have the number 8, and then it's going to do 8 times 7, okay, that's fine. But we also need to do 8 times 6, 8 times 5, 8 times 4, 8 times 3, 8 times 2, 8 times 1. And if we don't call the function again and again and again until n equals 0, then we'll never actually loop through all of the numbers 8, 7, 6, 5, 4, 3, 2, 1, 0. So you could do if else n is greater than, but we we don't really need to do that for this problem because we're only checking if it's one number. So return n times factorial n minus 1, and that is our recursive case here. And this is called our base case, right? Looking at the example here, we've got a base case and a recursive case. So that's what it will look like. So here, it should loop through all of the numbers from 8 until 0, multiply them, and give us this. So let's run it, and let's see what happens when I run it. It may take a little bit, depending on your computer's, whoops, my program's still running, processing speeds. And let's take a look here. What do we get? 40,320. Perfect. Now, let's say we put a really big number in here. Actually, let's save an int. Please enter for factorial calculation. So I'll just ask the user for a number here. All right. We won't error check this or anything, but oops. I need to give it a name. Int num, and we'll pass num here. And actually, I should make this an unsigned long, just to stay consistent. All right. Oops, cannot convert basic ostream char to long. Okay, we'll just do this. C out. Oh. C out. I need to do this, and then C in. On the next line, okay. All right. Gosh, it's been a while since I've actually done this. There we go. We just want to C in. Okay, C in to num. I need to make num up here. Unsigned long num. Initialize it to nothing. Then C in num. Perfect. That took a while. Okay. What am I doing? Oh, I set the wrong. There we go. I had the wrong thing set as my active project. Okay. So we are asking for a number for factorial calculation. Someone says they want to do 20. Let's do 20. Ooh, look at that. It's huge. Okay, let's run it again. Let's do 100. So this can do 100 times 99 times 98 times 97. Oh, didn't like that. Let's see if we do 50. Pretty big numbers. 100 was obviously too big. Let's try 90. Yeah. Anyways, kind of cool. That's recursion. So back to the PowerPoint. That's what we just made. That's our base case and our recursive case. If you don't have a base case, remember, you'll never exit the loop. It'll just keep going -1 into the negatives, into the negatives, into the negatives forever, and you'll have an infinite loop. So it's super important because that stops the recursion. Otherwise, it would just go indefinitely, and you'll run out of stack space and get a Stack Overflow error. So, all right, let's do another example, but with Fibonacci. All right, so going back to our code light here, and now, oops, Fibonacci. Let's talk about Fibonacci first from a math perspective. So Fibonacci is basically the Fibonacci of a number of 0 is 0. The Fibonacci of 1 is 1. That's our base case. So we know that those are the hard-coded values that we can check for our base case. But the Fibonacci of n, so 3, 4, 5, whatever, is equal to the Fibonacci of n minus 1 plus n minus 2. Right, so the Fibonacci of 2 would be 2 minus 1 plus 2 minus 2, which would be 0. So 2 minus 1 is 1, and 2 minus 2 is 0. So the Fibonacci of 2 is, let me see if I got this right. Fibonacci of 2 minus 0, 2 minus 2 should be 1. I can't do it in my head, but or 0. It might be 0. We have to see. Anyways, we'll run in our program and we'll actually check it. So let's take a look at what the Fibonacci in C++ would look like. And we can do it for 2. We can do it for a larger number as well. So same thing using namespace, whatever. We're going to just leave this here, but we won't actually call it from our main function. So, whoops. We can keep the variable the same, but then when we see out, we'll just call a new function called fib. Okay? And we'll do the same thing, an unsigned long, call it fib, and it expects an unsigned long of n. Okay? That's good. And inside here, we want to have our base case. So we know if n is 0 or 1 that we can exit the program and return it. So if n, we can check either, we can do an if else, or we can also just check if it's less than or equal to 1, and that solves it all in one line. And then we just return n, right? So if it's 1 or 0, it'll be equal to 1 or less than 1. We know it's positive because it's unsigned, so we just return n to the console. Now, we want to return the fib of n minus 1 plus the fib of n minus 2. And this is our recursive case, right? So let's take a look and see if this is similar looking to this, fib n minus 1 plus fib n minus 2. Fib n minus 1 plus fib n minus 2. Looks good to me. So we'll enter a number here, and then we will take a look at what we get out of it. So let's run it. And I know this still says for factorial calculation, but there we go. The fib of 2 is 1. Now let's try the fib of 3, which, if I do that in my head, should be 2. Things start to get funky, though, when you get into bigger numbers. So let's do the fib of 10. 55. Because 10 minus 1, you're going all the way from 10, 9, 8, 7, 6, whatever. But if you go 10 minus 1, which is 9, plus 10 minus 2, which is 8, so 9 plus 8, you get 17. But then you go back through it again, and you do, n has now changed to 8. So now we do 8 minus 1, which is 7, and 8 minus 2, which is 6. Actually, I think I can find a better way of visualizing it for you guys if it's confusing. I even think it's a little bit confusing. Visualize Fibonacci calculator. So let's do the Fibonacci of 10. Fibonacci sequence, here we go. Mathisfun.com is a great, and you may have heard of Fibonacci, like the golden rule. It goes up like this, so it's like exponentially making a spiral. So here's the rule. For 0, it's 0. For 1, it's 1. 2, it's 1. 3, it's 2. 4, it's 3. 5, it's 5. 6, it's 8. So on. 10, it's 55. So we can check our work. We know it's right. It's the golden ratio. That's right. That's where you've heard it before, the Fibonacci. Here, let's see if there's a way they actually show it step by step. See if this one shows it. I want to see if I can actually run the Fibonacci. So pretend it's 55. So then 9 is 34. So how do you get 55? Let's see, Fibonacci of 10. So they take the sum of its digits, right? So the first sum was 8 plus 9, which was 17, which we got. But then they continue to add the rest of the numbers. So let's see. Oops. So then you can see here 55, they add 34 and 21, that's 55. And so on. 21 and 13 is 34. 13 and 8 is 21. 8 and 5 is 13. That's how it works. I kind of forgot how it works. So we'll exit that. And now we'll try it for a large number. You want me to try 0? Sorry, Simon. Let's try 0. Oops. I got an error in my code because I typed the letter F. So let's try 0 in here because we're checking if it's n is greater or equal to 1. 0 is technically an unsigned int, so there you go, we get 0, right? So we know our if statement for our base case worked. Now, let's say we try to do the Fibonacci of 40. Check this out. It will take a second, and then you can see it comes through. Because it has to do all of the calculations up to 40 to add them. So if we do a larger number, your machine will hit its limits, but things like 50 are even exponentially larger than 40. So we can try 45, and look, it's taking a minute, taking a minute, taking a minute. And look at that, the calculation, you might hit an out of memory error, but it took that much longer just to go from 40 to 45. So if you did, 100 or something like that, you really could hit an out of memory exception, or it would just be, taking that long. So even if I did 42, 43, we can see it takes a considerable amount of time just to calculate recursion. So you do have to be careful with recursion because recursion is used for very specific problems. You don't want to use it all the time. So here's some important notes. Generally, you want to use an iterative solution where you loop through 0 to however many times. Usually, if you use an iterative solution on a recursive problem, it's less elegant and more difficult to understand the code. So for using Fibonacci and factorials and stuff like that. But sometimes we have to meet non-functional requirements, and that's what it takes. Okay, so if recursion doesn't eventually stop, you'll eventually have infinite recursion, so we need the base cases. Recursion can be resource intensive, as you saw. Just doing the Fibonacci of 45 took forever. Remember to include your base cases so it terminates. Only use it when it makes sense. So you don't want to use recursive problems all over the place because it can be memory intensive. And anything that can be done recursively can be done iteratively, but it can end up in errors if you use too much memory allocation. Cool. Any questions about recursion, guys, before I move on into header files? Does that make sense? Actually, before I move on to header files, I'll end this recording here, and then I'll talk about the lab. We're going to have a recursion lab just after this. So I'll start a new recording, and you can watch that in the next video. So I'll stop this.